Hello, my name is Cadet Captain Tanisha Lekanen. I am a 16-year-old student and I attend AIT High School in Connecticut. I am the team leader for Team 2979 Semper Vigilans, and my team and I are from Civil Air Patrol, Westchester Cadet Squadron 1, based in Scarsdale, New York. We would like to extend our gratitude and a thank you to our mentor Sam Dodson and to our coach Lieutenant Colonel Breland, and I will now be introducing you all to our team members.
Hi, my name is Cadet Second Lieutenant Yashwala Subramanian, and I'm a junior at Edgemont High School. My STEM focuses are aviation and space exploration. For the MIT CubeSat Challenge, I worked on programming and document managing.
Hello, my name is Cadet Chief Master Sergeant Frank Zing. I'm 16 years old, a junior at Rye Country Day School. My STEM focuses on aerospace, and I helped with the systems design and mission documentation for this project.
I'm Cadet Senior Master Sergeant Avantika Jain. I'm 15 years old and I'm a freshman at Darien High School. My STEM focus is on robotic engineering, and for this CubeSat mission, I've worked on software development and basic hardware.
Hello, I'm Cadet First Lieutenant Christian Metzger. I am a junior at Bronxville High School. I am 16 years old. My STEM focus is on aerospace engineering, and I worked on hardware for the CubeSat team.
Hello, I'm Cadet Captain Koop Abramovich. I'm 15 years old and I am a freshman at Rye Country Day School. My STEM focus is on engineering, and I worked on software architecture on software for our CubeSat team.
Our first SMART goal is to optimize CubeSat power consumption to ensure that no component exceeds 75% of the battery's capacity at any time, which would prevent system instability. To make this measurable, the battery state of charge will not fall below 25%. To make it achievable, we'll conduct rigorous testing and real-time monitoring of power draw. This is relevant because power failure would compromise mission success, making this a critical requirement. Target completion date is March 1st, 2025, allowing time for final adjustments. Our SMART goal number 2 is about link budget performance. This will ensure reliable image transmission under the worst-case signal conditions. To be specific, we'll aim for a minimum 5 decibel link margin to maintain transmission quality. This will be measurable as image data loss must not exceed 5% under adverse conditions. This will be achievable as using link budget modeling and simulations to verify our performance. This is relevant as reliable communication is essential for delivering high-resolution images. This is time-bound as we aim to complete this by March 1st, 2025, allowing time for adjustments. Our third SMART goal is to optimize the CubeSat's readiness. This will be specific as we'll fully test power, imaging, and data transmission to ensure 90% accuracy in disaster image classification. This is measurable as we'll ensure 80% system success, 30-second image transmission, and 75% battery efficiency in 3 test runs. This will be achievable as we'll use simulations, existing hardware, and expert feedback to refine performance. This is relevant as it ensures critical CubeSat functions work for disaster monitoring and emergency response. We will aim to complete this by March 1st, 2025 to make this time-bound.
Our mission is to capture and transmit images of flooded areas to support disaster relief efforts. The CubeSat will launch in March of 2026 from Florida and operate in a low Earth orbit LEO between 180 and 2,000 kilometers, optimizing power efficiency and data transmission speed. LEO provides radiation protection due to the Earth's magnetic field and ensures frequent revisits for rapid imaging updates. The CubeSat's core systems include ADCS, which maintains satellite orientation for precise imaging, communications, which transmits images and telemetry to the ground station within 30 seconds per transmission, EPS, which manages power storage and distribution, ensuring safe battery discharge levels and redundancy, and the radiometer, capturing high-resolution flood data with optimized spectral sensitivity, as well as command and data handling, which processes sensor data, managing system health, and automates safe mode recovery in case of a failure. Risk mitigation includes power budgeting, link margin and analysis, and fault detection to ensure continuous operation in dynamic orbital conditions.
This block design begins with the CubeSat ejecting into Earth's orbit at 7.8 kilometers per second. Solar panels convert sunlight into electricity stored in batteries and distributed as DC power, as the Raspberry Pi controls imaging, running code to capture images. Some power is allocated to the thermal system that regulates the CubeSat's temperature. Some power is allocated to propulsion, guided by the Altitude Determination and Control Subsystems, or ADCS, which adjusts positioning based on sensor data. Using a control loop, ADCS compares the target orientation with the CubeSat's current state, correcting errors through propulsion adjustments. This ensures stability and accuracy while compensating for disturbances. This block design details the imaging system's code. To minimize cost, the CubeSat captures only essential photos. It takes the first 2 images 24 hours apart, storing the location and name in the file name. An API call to the weather station checks for rain in the past or next 12 hours. If yes, the CubeSat sends the images to the ground station, where an LLM model determines if flooding occurred. It then switches to capturing images every 2 hours, transmitting critical data to the ground station. If a flood is detected, the ground station alerts emergency services. If not, it instructs the CubeSat to resume 24-hour image intervals, optimizing data use while ensuring valuable information is collected. The image on the bottom describes how we would communicate with the CubeSat through radios.
This is the software architecture. Some tasks required to be coded are positions and direction relative to Earth, taking pictures, how to adjust the direction facing, and downloading and uploading information. Some rough pseudocode would be, if the CubeSat is at a predetermined position and it's facing that position on the ground, then it will take 5 photos with a 10-second pause in between each one. We will be using Python for this project. Raspberry Pi can handle a moderate amount of code. Some factors that can alter this are SD card size, quality of cameras, and power supply.
Constructed within Tinkercad, our group manufactured a scale model that is an assembly of parts. Our group used a ruler to measure each part and model it individually in our CAD software. For our commercial components, we use models we found online. An example of this is the Raspberry Pi computer and the camera shown on screen in the third photo. After importing and crafting individual structures, we mated parts together to match our build from the kit. Once fully assembled to match the build, the computer was placed into a cubic structure in the second photo, 10 centimeters wide for each side, to match the guidelines of a 1U CubeSat. We then crafted a solar panel on the outside.
The table outlines power requirements for different operational scenarios. Each row details the energy consumption of various subsystems such as command and data handling, EPS, and ADCS, taking into account nominal power, contingency margins, and duty cycles. In science mode, power usage remains steady to support research activities. Downlink mode demands significantly more energy due to the transmission of data, and during an eclipse, energy consumption is reduced by deactivating certain subsystems, such as payloads, to conserve power.
Our total system mass is 1.1 kilograms, accounting for a 10% contingency margin. The electronics, including the Raspberry Pi, battery, and solar panel, weigh 480 grams and cost $93. The structure, made of acrylic panels and aluminum rails, adds 400 grams at $40. Fasteners and additional components contribute 95 grams and cost $10. Altogether, we keep the system lightweight, cost-effective, and within the budget at $143. Our link budget is dynamic and changes throughout the orbit. When the satellite is overhead, signal strength is optimal, but as it moves towards the horizon, path loss increases and the link weakens. If the ground station and satellite are not in line of sight, communication is lost, unless another station or relay is used. Doppler shift and atmospheric effects also influence performance, requiring continuous adjustments to maintain a closed link throughout the orbit.
The CubeSat project stores approximately 12.4 gigabytes of data per year, with a cost of about 2 cents per gigabyte per month, totaling 25 cents for 2,000 images. The number of images was calculated from past NOAA data on hurricanes and floods in Florida. Applications program interface calls to weather systems will be with requests of 200 to 300 bytes and responsive at 900 bytes per call. API calls to LLM model for flood detection handle 2,000 calls per year, transferring about 34.7 gigabytes of data, and both are free within the limits. This slide focuses on the uplink and downlink of the data from the CubeSat to the ground station. On my left side, the table shows how much kilobytes in data is used per system. The table shows Florida's flood and cyclone patterns, with peak flooding in August to September, with cyclones from June to November. A total of 2,051 images used 12.4 gigabytes, highlighting the need for focused data during hurricane season.
The power bank in the CubeSat is receiving power from the solar panels and transferring that power to the CubeSat through this wire. We know that the CubeSat has power right now because the lights in the Pi and IMU are on. The Raspberry Pi camera will take a picture of the before flooding scene displayed on our laptop and is able to do so because it is attached to a frame that is high enough. This is the after flood scene. Our CubeSat captured these images from NOAA's past flood data, storing them with local location and time. An API call to weather station confirmed rain in New York, triggering another image capture. Both images were sent to the ground station, where a large language model analyzed them and provided markings with additional data. With more time, the system could also send alerts to phones as a prototype for an app to notify citizens and emergency services.
Scaling to a flight spacecraft. First, we will replace the solar panel, increase transmission power, upgrade from UHF to S-band, choose low Earth orbit for better Earth imaging, replace the current camera, add thrusters, and adjust the velocity in the testing to match the Reynolds number.
When choosing an orbit for our CubeSat, we consider altitude, inclination, and orbit shape. Our satellite will operate at 400 kilometers for clear imaging and low collision risk. We'll select an inclination based on target coverage with higher inclinations allowing global access. A circular orbit ensures stable imaging. Other factors like synchronization with Earth's rotation and lighting conditions further refine our mission's effectiveness.
The lessons we've learned over these past 3 months have been absolutely invaluable. My team and I have gained a plethora of technical knowledge, skills in team building, time management, and persistence. But especially, we've learned of a new methodology to volunteer service, one of Civil Air Patrol's cadet core values. The trials and tribulations that we faced were expected, such as issues in communication and tricky code, but the real reward was creating solutions to overcome them. This challenge has certainly enriched my own leadership skills and overall taught our team of cadets more than we could have hoped.